Cathode ray tubes. A guy named J.J. Thomson. Again, we're in the 1800s to the early 1900s. He constructed what he called a cathode ray tube. So it's a glass tube that is partially evacuated, meaning it's a lower pressure inside than outside. And it's got electrodes at each end, and he hooked it up to a high voltage power source. So you've got a cathode and an anode, and the electricity is trying to flow through here, and it will. So he found that you'd get a beam of light. It looks like light. It's actually a beam of particles. He called those cathode rays because they come from the cathode. And here's an actual photograph of the cathode ray tube in action. So we see this green, looks like a green beam of light. Those are the cathode rays. They go from the negative electrode to the positive electrode. And he observed these cathode rays and found that the particles that compose those cathode rays travel in straight lines. They don't wiggle around or anything. They just go in straight lines. And they're independent of the composition of the material that they come from. You can make that cathode out of different metals, and the cathode ray is the same. It doesn't matter what the material is. He also observed that they carry a negative electrical charge. That's why they're leaving the positive electrode and they're going to the negative. Wait a minute. They're leaving the negative and going to the positive, sorry. They're repelled by the negative. So we need a basic understanding of electrical charges. Electrical charge is an intrinsic property of matter, and it has positive and negative. It's a lot like magnetic charges or forces, but it's not the same. But we have experience with magnets, right? Playing with Brio trains or magnetics toys or sticking magnets on the refrigerator, right? We have an idea of what magnets do. Electrical charges work in a very similar way. Opposite electrical charges will attract each other, like the opposite poles of magnets. They just stick together all by themselves. Like charges will repel each other. It's like you take those two magnets and you turn one of them around, and now it's really hard to push them together, right? It seems like magic. It's just science. Same thing with the electrical charges. And if you have charges the same magnitude, here a positive one and a negative one, they'll be attracted to each other, and together the overall charge will be zero. The basic principles of electrical charge. So this cathode ray was a negative electrical charge. So he was able to measure the charge to mass ratio of the particles in that ray by deflecting them using electric and magnetic fields. So by applying an electric field, he was able to make the beam move over. And using a magnetic field, he could also deflect it. And so by looking at how it was deflected, he could establish the ratio of the charge to the mass. And so what he observed is that 1 gram of these particles would have a charge of negative 1.76 times 10 to the 8th coulombs. Coulomb is just a unit of charge. It'll crop up a couple of times, but we're not actually going to do much with it. So negative charge, 1 gram of these particles had this amount of charge on them. He couldn't say anything about what the mass was or what the charge was on an individual particle, but he could measure the ratio. This implied that the particles in that cathode ray were about 2,000 times lighter than hydrogen. Hydrogen is the smallest known atom. So if atoms are indestructible, how can you have a particle that's smaller than an atom? This was a big deal. This was incredible. they thought of it as, okay, we took the indestructible atom and somehow we're chipping a little piece off of it. So we can take a little piece out of the atom. So this was a big deal. What he had discovered was the electron. So the electron is a subatomic particle because it's a particle that's smaller than an atom. Electrons are negatively charged, they have very low mass, and they are present in all atoms. All atoms have electrons. That's why it didn't matter what the metal was that he made that cathode out of, the beam was still electrons, because all atoms have electrons in them. So this was the first evidence that all elements are actually formed from the same particles. Millikan did an oil drop experiment, also looking into mass and charge of these electrons. He was an American physicist, so this is occurring in 1909. So this is an illustration of his setup here. So I'm going to describe this, and then we're going to watch a YouTube video that describes it, and then hopefully it'll make a little bit of sense. So here he has an atomizer, which will, like a perfume atomizer, will spray out a very fine mist of teeny tiny oil particles. Those oil particles are subject to gravity, and so they'll fall down in this chamber. Here he has a positively charged plate, and there's a little tiny hole in it. So the particles will fall down. Most of them will just land on the plate, and it gets all oily. Some of them, though, will fall through that little hole. They fall through the hole and then are hit by a beam of ionizing radiation, which causes them to be charged. So now these charged oil droplets are suspended in this electrical field between the positive plate and the negative plate down here. You adjust the difference in the charge here, and you can get the oil droplets to be suspended. So you've got gravity pulling them down, but you've got electrical field holding them up, because the negatively charged particle is going to be attracted to the positive plate. So electric field is pulling up, gravity is pulling down. And we've got a light source and a viewing microscope so that you can adjust this electrical field and get this particle to just be suspended in midair.
In a series of experiments carried out between 1908 and 1917, R.A. Millikan succeeded in measuring the charge of the electron with great precision. In his experiment, a fine mist of oil was sprayed into the upper chamber with an atomizer. Some of the tiny oil droplets fell through the hole in the upper floor, and Millikan was able to determine the mass of an oil drop from its terminal velocity. Next, Millikan used an X-ray source to ionize gas molecules in the chamber. Electrons from this ionization process adhere to the oil droplets. The oil droplets now carry a negative charge. The negatively charged oil droplets can be halted by adjusting the voltage across the two plates. As the voltage across the plates is increased, the velocity of the oil drops slows. As the voltage is increased further, some drops will begin to move upward toward the positive plate. If the voltage is set just right, an oil drop can be suspended. When an oil drop is suspended, its weight, mass times acceleration due to gravity, is exactly counterbalanced by the electric force applied. The electric force applied equals the applied electric field, E, times the charge on the drop, Q. Since the mass of the oil drop, the acceleration due to gravity, and the applied electric field are known, Millikan could solve for Q, which is the charge on the drop. Millikan found that droplets had different charges, but each was a whole number multiple of a smaller charge, equal to negative 1.60 times 10 to the negative 19th coulombs. Millikan concluded that this was the fundamental unit of charge, the charge of an electron. From the charge of an electron and the charge-to-mass ratio of an electron determined by Thomson using a cathode ray tube, Millikan was able to calculate the mass of an electron. The mass of an electron, 9.10 times 10 to the negative 28th grams, is an exceedingly small mass.
questions? I like to talk about this experiment because it gives us a little picture of how scientists go about learning stuff. We're not just measuring, oh, well, how big is this block of wood? We're trying to figure out how big is this particle that's too small for us to see. That's a puzzle, huh? That's not a simple matter. How big are these particles that are too small for us to see? What's the charge on them? And so you have to come at this indirectly. And a lot of this chemical history, I mean, these guys were brilliant. They came up with these very elegant and yet simple methods. They didn't have computers and all kinds of technology. They were just barely learning about electricity, right? Might still be, going around in a horse and buggy. They didn't have a car. So they established the charge of an electron and the mass of an electron. So each of those oil drops was a different size, but they could figure out the mass and the charge and the mass by how fast it fell, and the charge using the mass to charge ratio that Thomson had developed. So they found that the charge on each particle was a multiple of this same small number, because some of those particles had 2 electrons on them, some had 3, so a charge of -2 or -3 based on the number of electrons, but they were all multiples of this number. So this is the charge on a single electron, and this is the mass of a single electron. And those are not numbers that you need to memorize. But this number is, as the video said, exceedingly small. So that would be 0.0027 zeros and then 910 grams. That's a lot of zeros. It's very, very small.